bridging the performance gap between target-free and target-based reinforcement learning. In this paper that we published at ICLR in 2026, we focus on the role of target networks in reinforcement learning. This is why we start by counting the story of reinforcement learning with a special focus on target networks. Indeed, in 1992, Q-learning was introduced without a target network. This is because the setting was tabular, and there only one Q estimate is useful to learn a proper estimation of the Q of the action value function. Then in 2015, Deep Q network was introduced, and for the first time, a target network was used. It was used to compute the regression target, which is R plus gamma max of Q, but this estimator is using an old copy of the online network, which is over there. So here we have the target network. And from then, many works have picked up on this idea because it allows for stable training. So first, we have this target-based variant, which is using a separate copy of the online network, where the online network is composed of a feature extractor and a linear layer. The regression target is computed with the frozen part of the network and using the Bellman operator. If we kick out the target network, we end up having a target-free approach where the Q estimate is learning from its own value how to control the system. We really have this duality between target-based approach and target-free approach. And it has not been really clear which one to prefer. There has been still some ablations on many papers showing that target-free approaches lead to poor performances. So here's an example from the Bigger, Better, Faster paper, where when we remove the target network, we see that the performances are reduced. Similarly, in the paper Bigger, Regularized, Optimistic, when we remove the target network, we have a drop in performance. Interestingly, for methods that have been introduced without a target network, it's the case, for example, for Melomax, only a few years afterwards, we could see a follow-up work reintroducing the target network and showing better performances. This was the case as well for CrossQ, for which was introduced without a target network, and a follow-up work mixing CrossQ with weight normalization showed that by removing the target network, we actually lose performance. So the first contribution of our work is to properly establish that target-based approaches are usually working better than target-free approaches. So for that, we would like to show that target-based approaches have a higher performance, but of course have a higher memory footprint, because we need to store a separate copy of the online network, as opposed to target-free approaches, which usually have a lower performance, but have a lower memory footprint because it only needs to store one Q estimate. So we considered multiple benchmarks spanning from online to offline, from discrete actions to continuous actions, and also a text-based setting. We considered all of them, and we evaluated each time the relevant baseline. So for example, here it's DQN. For offline, it's CQL. For online continuous actions, it's SAC. And we used also ILQL for the text-based approach with GPT-2 architecture. We also kept an eye on the number of parameters used during training. So here the target base is represented as TB, and we represent target-free as TF. We see that each time we divide by 2 the memory footprint, which is usually seen as a preferable. However, we see that the performance drop is happening for every benchmark. So this confirms this intuition. And now we introduce a new approach, which is a happy medium between the target-free and the target-based approach. Indeed, here what we do is we simply have a shared feature extractor, and we build an old copy of the last linear head to have a smaller target network, but still a target network to hope for stabilization. Now that we've built a lightweight target network over there, we can actually use it to see if it performs well or not. But what we can be sure about is that we will keep a low memory footprint because the last linear layer is usually of small dimension. It is also interesting to see that with a target network, we can leverage the target-based literature and build on top of it. So we consider a variant in which we introduce the idea that is called iterated Q network that I also published at TMLR in 2025, where we take a head and we make it learn from the previous one. So here Q1 is learning from Q0 and Q2 is learning from Q1. I invite interested reader to look at this paper if they want more details. But here, one thing that is for sure is that we will keep the low memory footprint because once again, the shared linear, the linear layers are usually very small compared to the full architecture. So back to this board of benchmarks, we actually consider only using one head. So the first approach that we introduced, and we see that it usually helps bridging the gap. Here, for example, it fully bridges it. And otherwise it bridges it. It improves performances. And by including more heads into the architecture, so by learning more than one head at a time, we see that we gradually catch up on the target-based approach and even outperforming in some cases. But the main goal of this paper was to bridge the gap between the target-free and target-based approach, which happened in most of the benchmark. We see that the number of parameters did not increase significantly for the provided performance boost. I hope I convinced you that the performance gap can be bridged by sharing features and using this iterated loss. If you want more details, especially on how and why it works, you can look at this at the paper. You can also look at the code for more detail. And here is a follow-up work that also uses this iterated loss. Thank you for your attention.